Cover section 2.1, addition property of inequality. And you'll find that we are on page 46 of your book. They start off with a definition. That definition is an equation is a math sentence stating two quantities or expressions are equal. For example, here I have two expressions. I have 3 plus 1 equals 4. So I'm stating that this expression or quantity equals this quantity. And I have x plus 3 equals 10, which is stating that this expression is equal to this expression. And we call these math equations, math sentences, right? So this is what I call a closed sentence because it's very direct. 3 plus 1 equals 4. If I solve that, I'm going to get 4 equals 4 on both sides. So as you can see, if I had it on a scale here, if it was on this scale, the scale's balanced. This one is called an open sentence because I don't know what x is. It depends on what the value of x is to determine whether it is closed. If x was 7, we know 7 plus 3 is 10, the scale was balanced. But what if I said x was 4? Well, then I would end up with 7 and 10 on both sides. The scale would no longer be balanced. It would be destroyed. So we're going to talk about how we can keep these balances, manipulate these equations, and keep the balance so that it is still a true equal statement. Let's look at this first one. What happens if I add 5? So think of these as pounds. 3 pounds plus 1 pound, and this is 4 pounds. Well, what happens to this scale if I add 5 pounds, right? When I do that, this becomes 9 equals 4. All right, this is not true. This is a false statement, right? It's false. In fact, the scale probably now looks like this, right? It's no longer balanced. So I can't just add a number, and it seems to reason that I probably couldn't subtract also in a number without destroying that balance. So what can I do that would restore that balance? Well, let's look at it again. Take the same problem. If I added 5 to this side and I added 5 pounds to this side, then I end up with 9 equals 9. And you can see that on my scale, it's still balanced. I haven't changed the truth value. Sure, this is no longer 4, it's now 9, but I haven't changed the value or the truth value of the sentence. The sentence is still true. So it seems to reason that I can add numbers to the equation. As long as I do it to both sides, I will not change the value. Well, let's consider this statement here. Let's take 7 plus 3 equals 10. 7 plus 3 equals 10. All right. Well, what happens if I subtract 3 from one side? Okay, now remember, subtraction is like subtracting 3 is the same thing as adding the opposite. And we just learned that we can't add numbers. So if subtracting is like adding the opposite. Well, when I do that, this becomes 0, and I'm left with 7 equals 10. Well, 7 equals 10 is a false statement. So I can't just subtract to both sides, to one side. But if I do the same thing to both sides, if I subtract 3 here and subtract 3 here, right? Then I restore that balance. And so now I have 7 plus 0 equals 10 plus a negative 3, which is 7. And 7 plus 0 is 7. I still now have a truth statement. So it looks like then I can also add the same thing. But what you didn't realize here, what happened when I did this? When I subtracted 3, I ended up making a 0, didn't I? Here I just took some random number. But here I chose to subtract they were adding 3, I chose to subtract 3. So I chose to do the opposite, and I made a 0. Well, why is that important? Well, let's go back and look at our open sentence here. I have x plus 3 equals 10. Now, my goal is I want to find out what x equals that would make this a true statement. Again, you all know that it's 7, right? And you're smart enough to know and make an educated guess. But I need a process that is going to, when I have more complex numbers or bigger numbers, that I could figure this out without just guessing. So what I'm going to do is I'm going to say, okay, I'm looking at the x. They are adding 3 to the x. In order to get x by itself, I must get rid of this 3. I can get rid of this 3 by subtracting 3, because 3 minus 3 is 0. But remember, I just showed you, you cannot just add or subtract a number to one side. You destroy the balance. So since I subtracted 3 from this side, I must subtract 3 from the other side. So 10 minus 3 is 7. And we end up with x plus 0 equals 7. X plus 0 is 0. And I've just now solved my equation. That the solution set, or the only number or value that's going to make this a true sentence, is if x is 7. Now, do a check step. If I do a check step is going to be what? I'm going to take the original equation, the x plus 3 equals 10. I'm going to substitute in 7, which by the way is the same problem that we just did over here. And I'm going to check it, and I get a true statement, so it checks out that the solution set is 7. Now there's different ways. Now that we found out that the value that makes this true is 7, we will write our answers like this. The solution set, and you use your brackets, is 7. And so you make it in a roster form, the solution set. Another way you could also write your solution for this particular equation. Remember, we're dealing with this equation. The solution set for this equation is 7, or you can graph it, right? 1, 2, 3, 4, 5, 6, 7. Here's the 7 mark, and you could graph it as well. And so that's the two ways that you could write your solution. The solution is 7, or you can graph the solution as 7, which leads me into the next definition. Solution is the value that makes the sentence true. The only value that made this true was 7. So 7 is my solution. Let's look at example 2.1a on page 47. It says, determine if x equals 2, is it a solution to each equation? Okay, so here's the first equation. They want to know, is 2 a solution? When they give you an open sentence and they give you a given value, the only thing you can do is evaluate. So I'm going to plug in 2 for every place there's an x. Now I can write this as 5 times 2 minus 2 equals 8. Because remember, a letter next to a number means multiplication. So I can use this now to indicate multiplication. Or I could use a parentheses, 5 times 2, to indicate multiplication. Once I do that, I simplify. 5, and I have to do my order of operations, which means what? We multiply before we subtract. So 5 times 2 is 10. 10 minus 2 is 8. So this is true. So if this is true, then I can say yes, right? That 2 is a solution, right? So I can write it. 2 is the solution, right? Let's look at the next example. Here we have x plus 3 equals 6. Again, they want to know, is 2 the solution? So I'm going to plug in 2 for my x's. Simplify. 2 plus 3 is 5. 5 equals 6. Okay, this is a false statement. So I would say no, 2 is not a solution. Okay, so that's how you can determine on that. Then we have another definition. It says equations that are straight lines when graphed are called linear equations. So when you're graphing and you get a straight line, that's representing a linear equation. Well, what is a linear equation? A linear equation that has one variable and it's raised to the first power only. Well, here's a linear equation. We have the one variable, we only have x. I could have an x over here. I still have only one type of variable, right? And they're raised to the first power. If I had x squared plus 8 equals 3, this is no longer a linear equation because it's to the power of 2. So remember, a linear equation is represented with one variable and it has the first power. Now, to solve this type of a linear equation, you must isolate the one unknown variable. So here are the steps that I'm going to give you, but we're going to do several types of examples. 1, you simplify both sides. 2, you get all the variables to one side of the equal sign. And 3rd, you isolate the variable by making either zeros and ones. And we've already discussed about how you make zeros. So let's look at this example. The first thing I'm going to do is, can I add x to 8? No, they're not like terms. I can't. And is there anything to do over here on this side? No. So there isn't anything to simplify. Okay, is there more than one x? No, there's only one x, and it's already on one side of the equal sign. So next thing I'm going to do is step 3, which is isolate the variables by making zeros or ones. Well, today we're only discussing on how to make zeros. So I look at the x and I'm saying, okay, what are they doing with the x right now? They are adding 8. So in order to make this 0, I must what? I must add a negative 8 or add the opposite. So I'm going to put this in my margin that I'm adding the negative 8. So if I take this and I add a negative 8, and I remember I have to do it to both sides of the equation where I'm adding the negative 8. What happens here is this becomes 0, and x plus 0 is x, and 3 plus a negative 8 is a negative 5. And so x then, we're assuming that the solution set for x is negative 5. Well, let's do a check step and let's check that, okay? How do we check it? We take the x plus 8 equals 3, the original equation. We plug in our solution, negative 5 plus 8 equals 3. And negative 5 plus 8 gives me a positive 3. This is a true statement, so it checks. X equals a negative 5 is true. You could also graph your solution, which we'll get into graphing more. Whoops, I'll put my 0 here. 1, 2, 3, 4, 5. This is a negative 5. And I could put a dot. So there's 2 ways I can slow my solution here. All right. All right, so again, to keep the 2 sides balanced on the equal signs, whatever is done to one side must also be done to the other side. So keep that in mind. And so this, what we've been doing, is called the addition property of inequality. That addition property of equality formally states this: that given A, B, and C, where I tell you that A and B are equal, and C is some value, any quantity, okay, any quantity, then I can add C to both sides, A plus C and B plus C, and they're still going to be equal. I can also subtract C from both sides, and it's still going to be equal. So that's what that addition property of equality is. The equation will remain true, right? And what we're really doing when we're solving is we're making zeros. So let's look at this example. 2.1b on page 47. It says solve for x. So here I have x plus 2 equals 10. Now off to my margin here, I'm just going to note here, okay, what are they doing with the x right now? They're adding 2. So in order to get rid of this 2, because my goal is to isolate or get x by itself. So they're adding 2, so I'm going to add a negative 2 to both sides of the equation. So I'm going to write x plus 2 plus a negative 2 and 10 plus a negative 2 because I'm adding a negative 2 to both sides. 2 plus a negative 2 gives me 0, right? And x plus 0, this 10 plus a negative 2 gives me 8, and x plus 0 is x, and so I get x equals 8. I've now isolated, right, that variable. They aren't doing anything more to this variable, and I now know what the value is. It is 8. So I'm assuming that my solution set for this is 8. But let's do a check step. Check step says that I take the original equation, I substitute in my solution for wherever there's a variable. So here I have 8 plus 2 is 10. 10 equals 10. This is a true statement. It checks. So therefore that's my solution. And I could also graph it as well. Okay? So I'm looking for, when you show your work, I'm looking for you to show your work, right? I'm looking for the check step, and then I'm looking for your final solution. Let's do another one. Example 21.c. It says solve for n. Now remember, you don't always have to work with x's. You can get different variables. So we're going to look here. We have n minus 10 equals 2. My goal is to get n by itself, right? Well, they're subtracting 10, so I'm going to add the opposite. I'm going to add a positive 10 to both sides of the equation. So n minus 10 plus 10 equals 2 plus 10. I've kept that balance. A negative 10 and a positive 10 give me 0, and n plus 0 gives me n. And that 2 plus 10 gives me 12. So I now know that n is 12. Let me do a check step. I'm going to take my original equation, plug in 12, and check to make sure that I didn't make any mistakes. And I end up with 2 equals 2, so that checks. So this is true. So I can now say my solution set is 12. Okay? All right, next one. It says, on example 2.1d, page 48, solve for y. All right, we have fractions. No big deal, right? Don't let fractions scare you. You know, when you're adding and subtracting fractions, you have to have common denominators, but the process for solving is just the same. Again, your goal here is to get y by itself, right? So what are they doing with the y right now? They are subtracting 3/5. So I want to do the opposite of subtraction, and I want to add a positive 3/5. If I add a positive 3/5, I have to do it to both sides. So I'm going to write y minus 3/5. I'm going to add 3/5, and I'm going to add 3/5 over here. Well, negative 3/5 plus 3/5, again, I made a 0, didn't I? Right? So I got y plus 0, which is y. Over here, though, I now have to add the 1/3 plus the 3/3. I cannot do that unless they have a common denominator. So if you don't remember how to do that, we kind of covered it a little bit at the beginning. There are some additional videos you can watch. But I'm going to multiply this fraction by 5 over 5. I'm going to multiply this fraction by 3 over 3. Remember, I'm multiplying by 1. You can multiply 1 by anything and you don't change the value. So Whoops, I'm sorry. Let's switch that. I'm going to multiply this by 3 over 3. And this one by 5 over 5. So 5 times 3 gives me 15, right? And 5 times 3 gives me 15 on the bottom. On the top, 5 times 1 gives me 5. And 3 times 3 gives me 9. And now I can add, because I have common denominators, 5 plus 9 is 14. So I get 14/15. All right, let's do the check step. We might have made a mistake. Who knows? We may have made mistakes up here. So we're going to take our original equation. We're going to substitute in our answer, 14/15 minus 3/5. And we're going to simplify. Well, I cannot subtract these because they don't have a common denominator. But if I take this 3/5 and I multiply it by 3 over 3, because 5 times 3 is going to give me that 15 I need on the bottom, I end up with 14/15. 3 times 3 is 9/15 and 1/3. Well, 14 minus 9 gives me 5/15. And 5/15 reduces down to 1/3. So this is true. It checked. That means that this is our solution. So I can say the solution set is 14/15. Okay? So don't let fractions scare you any at all. The next example problem they give you is they're giving you decimals. It's the same process for solving. Solve for x. Again, they're adding a 0.4 to the variable. So that means I want to add the opposite, which is a negative 0.4. So I'm going to do that. Add 0.4 plus a negative 0.4, right? Negative 0.5 minus 0.4. Okay, I could write it that way. There's another way I can write it. When I get a problem like this with my decimals, you have to line up decimals anyway. So I like to do it this way. I'm going to add a negative 4, right? So I'm going to add a negative 0.4, right, to both sides of the equation. Well, this gives me 0, and I'm left with x. And then a negative 0.5 plus a negative 0.4. You got to pay close attention to your signs. You have two negative signs, so technically you're going to add and get a negative 0.9. And remember, with decimals, you have to line your decimals up. And so you end up with x equals a negative 0.9. Well, let's do our check step. We take our original equation. We substitute in our what we think our answer is. Right? Well, remember, this is negative 0.9 and a 0.4 positive. We got to line them up. Make sure you line up your decimals. And here you subtract, you get 5. This is the larger absolute value, so you end up with a negative 0.5. Negative 0.5 is the same thing as negative 0.5. So this is true, so it checked out. So now your solution is a negative 0.9. Okay, so don't let fractions and decimals deter you any at all. So let me go over the steps again. Even though we haven't applied the steps 1 and 2 yet, let's do some problems where we have to do that. Steps for solving. This has to do with solving for the unknown. First of all, you simplify both sides of the equation. You get the variables to one side of the equation, and then you isolate the variables by making zeros and ones, and the opposites, or do opposite operations, is what the zeros and ones are. So here's the first one. Here's my first problem. I'm going to look at the left side only. Okay, looking at the left side, can I simplify? Can I combine negative x plus 1? No, I can't simplify. So I'm going to look at the right side. Can I simplify anything? Sure. Negative 2x. Here I can multiply the 2 times the 3 and get 6. So now bring this straight down. So I've done this step up here. I have simplified both sides. Once both sides are simplified, then you need to get all the variables to one side of the equation. Well, notice I have an x here and an x here. So I need to get them all to one side. So since they are subtracting a 2x, to move that to the other side, I'm going to do the opposite, which is add 2x to both sides. What happens is this becomes 0, and I'm left with 6, right? 6 equals, what's a negative x plus 2x gives me a positive x. Bring everything straight down. So now what I've done here is I've gone from having the variable over here, it's now combined to this variable over here. And what did I did? I added the opposite. I'm still doing the same thing. This was a negative 2x, right? So I added a positive 2x. I added the opposite. Now all the variables are on one side of the equation. So now I'm ready to isolate variables by making zeros and ones. So I'm going to get this. My goal here again now is to get this x by itself. They are adding 1. So I'm going to add, right, a negative 1. So I'm going to add a negative 1 to both sides of the equation. 6 plus a negative 1 is 5. Positive 1 plus a negative 1 is 0, and x plus 0 is x. So here's my solution. My solution set is x equals 5. And you could do a check step here. And I'm not going to take the time to do the check step, but I am going to go to the next problem, which is your last exercise in the book. And it's, again, it says solve for x. So again, you're going to look on the right side. Can I simplify anything? No. On the left side, can I simplify? Yes, I can multiply or I can distribute this 2 out. So 2 times x is 2x, and 2 times 3 is a negative 6. Once I have simplified both sides of the equation, I now need to make sure all my variables are on the opposite side. So this is a positive x, so I'm going to add, this is a positive x, so I'm going to subtract x from both sides. This gives me 0, so I'm left with a negative 4 equals, bring down my negative 6, 2x minus x gives me a positive x. I now have only one x on the side. So now I'm going to isolate. They are subtracting 6, so I'm going to add 6 to both sides. And I end up with x equals a negative 4 plus 6 is a positive 2. And we could do a check step and to double check to make sure that that's true. But due to time, I'm not going to do the check step at this point. You can look at your exercise in the book. They have done that for you.